All right, guys, today we're doing Alchemy 16. This is the Chem Catalyst, and even though I'm not here today, you're going to do this the same way. So please go ahead and press pause on the video. I want you guys to try to fill in the blanks. So we're going to determine the identity of this daughter nucleus. This is the daughter nucleus right here. That's what we're talking about. After this fission process occurs, where this atom splits into this one, which is described down here, and this atom right here. Go ahead and press pause and fill this out on your Chem Catalyst sheet. Go ahead and take about 2 minutes to do that. And hint, you're going to need a periodic table. All right, so we're back. Let's see how you did here. I'm going to go over how you would solve this, and that really is, this is the goal of the lesson today. We want to be able to predict what's going to be produced when atoms undergo the nuclear processes of fission and fusion. So if I have iridium here and it has a mass of 93, and I lose 4 mass particles, 2 protons and 2 neutrons in this helium nucleus, this is going to have to, the other particle that's produced is going to have a mass of 189, okay? Because 4 and 189 is 193. That all adds up together. And I also need to know that I'm going to take care of all my subatomic particles, so therefore 2 and whatever this number is has to equal 77, so that would be 75. All right. Now, I can't use the mass number to identify the element. I'm going to use the atomic number, which 75 is, I'm looking at my periodic table here, is rhenium. So that's Re. So now I figured out that when iridium 193 undergoes alpha decay, that is, it emits a helium nucleus, I'm left with rhenium that has a mass of 189. Alpha decay, as I talked about in that last slide, is one of the types of radioactive decay that we're going to need to learn in this lesson. But alpha decay happens when an atom emits an alpha particle, and this will always be an alpha particle. It'll always have this composition, and it's sometimes also abbreviated with this little symbol here, which is alpha. So anytime you see this, what you really mean is you have a helium nucleus. These two can be used interchangeably. And if you'll notice here, if something emits an alpha particle, the mass numbers, so 189 and 4, are going to add up to 193. And the atomic numbers will also add up as well. So that's one type of nuclear decay that we're going to work with today. The other type is called beta decay. All right, beta decay is a little bit different because this is our beta particle here. You can see that I got my beta particle right here, right? And the abbreviation for that is the symbol beta. So these two things are interchangeable. If you see this, what it means is this. If you see this, it means that. But notice that the process is the same. So if mercury 197 undergoes beta decay, I write the beta particle, and look, what happens here is I have the mass number, the mass change is 0, so 0 plus 197 is 187, and this is a -1, so -1 and 81 equals 80. All right, and actually, if you think about this, how's the atom changing? Well, if I'm going from 80 to 81 in the atomic number, but I'm not changing the mass, what's happening is I'm having a neutron that's being converted into a proton. So a neutron is changing into a proton in beta decay, and a high energy electron is ejected from the atom. All right, so we've talked about 2 types of radioactive decay so far. We've talked about alpha and we've talked about beta. You guys are familiar with X-rays. So X-rays can also be emitted from atoms. We're not going to talk about them today, but X-rays are penetrating radiation. This shows the relative penetrating power. Where alpha and beta, they don't have much of a penetrating power. A thin foil will block beta. But X-rays and these are gamma rays down here. These are powerful. These are the dangerous, very dangerous types of radiation. They can even penetrate foil, and they'll be absorbed by lead, but even gamma rays can penetrate lead to some extent. Now, it turns out that when we look at radioactive decay, for our radioactive elements, like let's say uranium-238 here, this is a decay series which shows kind of like how this uranium will decay. And notice it's not always a one-step process. So this is hard to see, but that's a little alpha sign right there. So uranium-238 will actually decay into thorium-234 via alpha decay. So you can't really see that, but that's an alpha decay right there. And then that will convert to Pa-234 back to U-234 through the process of beta decays. So in this case, notice the atomic number is increasing because we're converting a neutron to a proton, so the atomic number gets greater. Then once we get back to U-234, we can go under an alpha decay to thorium-230, another alpha decay, another alpha decay, another alpha decay, another alpha decay, where it gets to a kind of lead, and then it goes to bismuth and to polonium, which both can alpha decay themselves and further beta decay, and ultimately the end product here is lead. And this is important because ultimately things that decay radioactively, they will decay until they hit lead, because lead is the last stable element that most of them will end up turning into. These decay processes are also described by half-lives. We're not going to talk about that in this lesson, but this could take anywhere from a fraction of a second to thousands and thousands of years to go from, say, uranium-234 to thorium-230. And this step might take a fraction of a second for half-life, and this might take thousands of years. It just all depends upon the stability of these individual nuclei. So we've talked about fission, we've talked about alpha decay and beta decay. Excuse that. Let's look at fusion. So elements can also be produced through the process of fusion, and this takes place primarily in stars in the universe. And you can see here what fusion is. It's just the combining of lighter elements into heavier elements. But notice, look, 4, atomic mass, 4 plus 4 is 8, and 2 plus 2 is 4. So it's pretty simple. So in the sun, we can fuse helium atoms into beryllium, and that releases energy. Our sun is currently doing that, and that's what's providing the energy for the sunlight outside, and also the heat which keeps our planet warm. And then you can see beryllium fuses with helium to make carbon plus energy, and you can see here that carbon, when fused with helium, to make oxygen and energy, and so on and so on. And this will go up to iron. So this will produce these elements up here on the periodic table, all the way up to iron. But you notice that's only part of the story. There's a lot more elements on the periodic table. I mean, iron's only element number 26. So how do we get the other, 92 elements that naturally occur? And that happens through supernova. And you might remember that from the game that we played yesterday, that in supernova, what happens is a star explodes and it kind of spits off all of its elements. But it also provides energy enough to fuse the heavier elements on the periodic table that we have here, colored in there. So that's a quick little tour through radioactive decay and fusion. And I want to close today with just a little bit of practice. So I need to make this visible first of all. So this should be visible to you. We're going to go through and fill out the blanks, and then you're going to work on lesson 16 in class. And hopefully you'll have this ready when I get back. But if we look at these practice problems, what we're trying to do is fill in the blank. So what type of decay is this, alpha or beta? Well, it's got to be beta because that is a beta particle. So how do we figure out what goes in the blank here? Well, -1 plus what equals 84? Well, that's got to be 85, right? 85 and -1 is 84. Element 85 is astatine. So this would be AT. And then up on top, it's just 209 because 0 plus 209 equals 209. So that would be that equation represents the beta decay of polonium 209. Down here, what's this? It's an alpha particle. Okay, so again, this would have to be 57 because 57 and 2 is 59. So element 57, if I can find it here, that shouldn't be too hard. 57 is lanthanum, La. And on top, this is a 141. That's pretty sloppy. Sorry about that. So this would be 137. 137 and 4 is 141. So praseodymium will alpha decay to form a helium nucleus, and then this daughter isotope, which is lanthanum 57 or lanthanum 137. Now, this is interesting. We're filling out what undergoes beta decay. Well, what I like to do here is just kind of right underneath. Okay, so what's a beta particle? It's an electron with a -1 atomic number here. So if this is going to take place, if it's going to undergo a beta particle, 20 plus -1 must be 19 here, right? And element 19 is potassium. And then on the top, 40 plus 0 is 40. So I've got potassium 40. That's what that would be. 20 -1 is 19. And 40 equals 40 plus 0. So these are the types that are discussed on your handout today. We've got, like we said, we've got beta decay, 2 examples of beta decay, an example of alpha decay. But we also have this situation here. We've got to fill in this blank. There's only one possibility here. I don't have an alpha particle. I don't have a beta particle. So this must be fusion. And these are the easiest ones, because in fusion, you're basically just taking the atomic masses and adding them up. So that would be 16, and that would be 2 plus 6 is 8. Then look at your periodic table and oh, that element is oxygen. And so there we go. Okay, so I know that was fast, but I think you have enough information to work on lesson 16, which is old gold. So go ahead and work with your partners and complete lesson 16, and I will check that when I get back to class on Monday. Good luck, guys.